So, hi everyone. As you heard, my name is Michael Green, and I'm indeed here to tell you about a different approach to building algorithms and building machine learning methods, really. I'm also going to argue that they are fundamentally the same thing, and you'll see that a little bit later in my talk. But let's get cracking. Basically, I'll talk about the overview of AI and machine learning, and I'm not the first one to do this, and there are lots of people who have their take on it, but this will be my take. I'll also try to extend to you the idea and concept of why this is not enough. We are very good at telling ourselves that we have come really far in AI, and I would actually tend to disagree with that. I think we're playing around in the pedaling pool, and it's simply not good enough. We need to innovate this area, and we need to be better. I will also talk about how perception versus inference can work in a computer. I will make a short note about our Bayesian brains, because that's fundamentally how we reason as people, at least from a macroscopic perspective. I'll also talk a little bit about probabilistic programming and why I see that as a very key point to marrying two very different fields or differentiated fields today. And in the end, I'll tie all of it together so that you can see how you can actually practically deploy a solution like this. But basically, if we just go back to basics, so I know a lot of different definitions of artificial intelligence. There are a lot of them out there, and none of them says the ability to drive a car while not crashing. That's simply not artificial intelligence. That is something that solves a domain-specific problem that is challenging, yes, but it's not AI. Neither is diagnosing a health disease in a patient that comes into the ER. That's also not AI. Neither is actually what I do in my company. That's also not AI. All of those are examples of narrow AI, where we try to use machines to do more clever things than an individual person could do at the same task. But my definition of AI is basically that it's sort of the behavior as shown by an agent that you stuff into an environment. And that behavior in itself seems to optimize the concept of future freedom. Now, that is the closest definition to artificial intelligence that I can come to, because that doesn't say anything, optimize the least square error, do back propagation to make sure that the cross-entropy error looks good. All of those things are man-made, and I assure you, our brains do not do back propagation. It's simply not true. No one is telling our children how to stand up. They're not getting smacked on the hands for failing. My son, he failed several times this morning, but he actually succeeded when I left the room. So without my encouragement, he actually did better. That might say something about my pedagogical skills or the fact that he doesn't need my training to do these things. So there's a fundamental thing that's missing. There's a missing piece in our understanding of how knowledge is represented, accumulated, and acted upon. And that is what fascinates me more than anything. I'm sure you've seen this before. It's just a definition of what AI is today. So AI is a lot of things, but basically, we are in the top level there. Every single application you have ever seen, heard of today is in this field. Artificial narrow intelligence. There is no such thing as artificial general intelligence. It doesn't exist today. And if someone says they have it, they're lying. Because we don't have the representation of how to capture knowledge. No one has that. You simply cannot express this in Python or R or whatever language you want. It doesn't exist. We need to figure out how to represent this. So artificial general intelligence, that is really the task of saying, how could we actually take an AI that knows how to drive a car, stuff that into a different environment, and make it utilize the skills that it had learning how to drive the car and apply that to a completely different field. That is domain transfer, and that is something that no AI can do today. Now, artificial superintelligence, and the only reason I'm mentioning this is because it's really, really far away. The only thing super about it is how super far away it is into the future. And there's been a lot of people, battling about this. One of the famous guys, Elon Musk, he's more of a doomsday kind of guy with respect to this, and he should be, because that gets him money into his company. So it's a very smart move that he says that AI is going to destroy the world, so I'm creating a startup that's going to sort of regulate that. So imagine how hard it was to raise money for that venture. There are other things to consider about superintelligence, and that's that it is conceptually possible. It is something that sooner or later, if we do capture how to represent knowledge, how to transfer knowledge, how to accumulate knowledge, if we know that, then there's no stopping us from deploying this into the world. And for all practical purposes, now sounding a lot like Musk, what we released at that time would basically be a god to us. And the whole thing, and the scary part about that is, will it be a nice god? Nobody knows. But then again, there's very little proof in history that intelligence feeds violence. So if anything, the world is a safer place than it's ever been before. And I would like to see that as an evolution of our intelligence, as an evolution of our compassion. I don't see intelligence being a necessity for murderous robots. So I'm not very afraid of that scenario. I know we won't be the smartest cookies anymore in the world, but maybe that's not so bad. That was always going to happen, and evolution will make sure of that no matter what. But basically, the landscape looks like this. So you have this term, artificial intelligence, that's sort of ubiquitous and describes everything from doing a linear regression in Excel to a self-driving car to identifying melanoma on a cell phone. And all of these things are not artificial intelligence, but it's just become a buzzword, just like big data. I very much agree with the previous speakers about this. The way I see it is that AI today is two things. It's perception machines and there's inference machines. And by inference, I don't mean forecasting or sort of prediction. I mean real inference, where you actually predict without actually having any data. Now, under the perception part, we've come a long way. Perception machines are everywhere. Those are the machines that actually know how to drive a car. Those are the machines that know how to identify the kites in the images that we saw. All of those deep learning applications, they're basically perception machines. They can conceptualize something that they actually get as input, either through visual stimuli or auditory stimuli. They can sort of categorize it, but they cannot make sense of it. And I'll show you examples of that. And that's why I reason that we need more. We need to move into proper inference where we actually have a causal understanding, a representation of the world that we're living in. And only then can we actually talk about pure intelligence. But we can get closer, and I'll show you how to do that. The biggest problems in data science today, which is also another term for applied artificial intelligence, is that data is actually not as ubiquitous and available as you might think. For many interesting domains, there is simply no data. And the data that's there is exceedingly noisy. It might be a flat-out lie. It might be based on surveys, and we know that people lie in surveys. That's also a problem. Structure. The problem with structure is also that how do you represent the concept in a mathematical structure? Not necessarily in parameter space, but just structurally. How do you construct your layers in a neural network, for example? Identifiability. What I mean by that is that for any given data set, there are millions of models that fit that data set, generalizes from that data set equally well. And many of them do not correspond to the physical reality that we're living in. So there are statistical truths, parameter truths, and there are physical realities. And they're not the same thing. That's why my previous field, theoretical physics, is sometimes problematic, because quantum theory that I sort of specialized in, that has many different interpretations, and nobody really knows what's going on. But we know we can calculate stuff from it, so it makes sense in the maths. But as soon as we push this button, but what's really happening, then well, we're basically screwed, because no one knows. I mean, a lot of people like to pretend that they know. And then there are some people like the Copenhagen interpretation that says that, well, just shut up and do the math. which is basically don't ask the question because it cannot be answered. Hawking adheres to this school, by the way. He's also one of the guys who's super scared of superintelligence, funnily enough, because he's a clever cookie. There's also the thing about priors. So every time that you address a problem as a human, whatever problem I give you as an individual, you will have a lot of prior knowledge. You will have a half or a whole life, depending on how old you are, of knowledge that you've accumulated. This knowledge might be transferred from another person that they just told you about something, but you can apply this knowledge to the problem at hand. You can represent that knowledge in the domain of the problem that you're trying to solve. And that is something that we also can actually mimic today through the concept of priors. And that is basically the way of encoding an idea or a sort of knowledge as a statistical prior and as a statistical distribution that can be put on par with data. I'll show you later how to do that as well. The last part, but not the least important one, is uncertainty. I cannot stress enough how important uncertainty is to do optimal decision making. You basically cannot make optimal decisions without knowing what you don't know. And I'll stress that point several times during this talk, during the remaining 39 minutes of it. It's really great. I can actually see how little time I have left. So I will not show you more equations, and it's not because I'm particularly fond of them, but they do help express ideas. So in the top level, that's basically a complete, compact way of describing any problem that you might approach. It's basically a probability distribution over the data that you're fed. They are the x's. The y's, those are the things that you want to be able to explain. And the thetas, they represent all of the different parameters of your model, stuff you don't know. It can also be latent variables, concepts that you know exist, but that you don't have observational data for. All of that is a definition of a problem space. Now, what machine learning has traditionally done, ever since Fisher, is basically that they looked at this with a question that everybody knew was wrong. They basically said that, what is the probability distribution of the data that I got, pretending that it's random, given a fixed hypothesis that I don't know, that I'm actually searching for? So then the problem actually became, for all machine learning applications, which sort of hypothesis could I generate that's the most consistent with a data set that looks like my data set, but that's really not my data set? And you can ask the question, is that a reasonable question? And then I will tell you, it is not. It is poppycock. That question is not worth asking. Why? Because you're basically just trying to find explanations to fit your truth. That is not science, ladies and gentlemen. There's only one way to do science. You postulate an idea, and then you observe data to see if you can verify that idea or disregard it. You cannot look at a data set and generate a hypothesis that best explains it and think that that somehow has any physical representation in this world, because it doesn't. And that's why a lot of machine learning approaches, a lot of statistical approaches, has actually figured out, after several years of hardcore science, they found out that the biggest risk for dying from coronary artery disease is actually going to the hospital. Yeah, that's just not true. And nobody stopped and said, why did this happen? Is it because the researchers are brain damaged? Could have been the reason, but it wasn't. It was the methodology. It was they were asking the wrong question. Because if you ask that question, I can assure you that before you died at the hospital, you had to go there. So this makes perfect sense, but it has no representation of the problem you're trying to solve. What you should have said is, given that you're sick and you go to the hospital, and given that you actually have something that's worth visiting the hospital for, now that is predictive of you being actually disposed to dying for coronary artery disease. So how do we fix this? We fix this by doing what we should have been doing from the beginning. And this is not new. This formula down here below asks a different question. What does it ask? It asks, what is the probability distribution of the parameters of my model that I don't know, by the way, given that I have observed a data set that is real, it is not fake, it is not random, it is a data set that has been observed. What is the probability distribution of my parameters? Now that is an interesting question to ask. And that is a scientific question to ask. But what does that require? It requires you to state your mind. The last part on the denominator, which is the p theta given x, that says, what do you believe is true about your parameters given the data set that you have? And that's very, very important, ladies and gentlemen, because this is the difference between something great and something completely insane. Now, then you might ask, but okay, why didn't we do this? Because it couldn't be done. We simply didn't have the computational power to do this. And it's not because of the guy to the right-hand side there. It's also not to the guy on the left-hand side in the denominator. And you can see that the guy on the left-hand side in the denominator is exactly what machine learning is doing today. Now, why is that? It's because of the fact that they knew that the guy in the denominator, that is an integral from hell. And it cannot be solved. It looks at every single value of every single parameter that you have and sums that out. Now, this will end up in a scenario where you have to calculate a lot of more things than the number of atoms in the universe. And there are a lot of atoms in the universe, even the part that we can see. But that basically meant that all of this is out of the question. So someone realized, hey, but I don't need to calculate that. I don't care about probabilities. You know, I can just say that the point that is the maximum will be the same because the other thing is just a normalizing factor. It's a constant. Okay, good enough. We remove that. So done deal. And then they said, oh, but the prior, yeah, but what if I don't know anything? What if I don't want to say anything? I don't want to, you know, state my mind and, you know, put my knowledge into the problem. So that's just a uniform distribution over minus infinity and infinity. And whoop-dee, this equation here has been transferred to only the likelihood. But you made a lot of assumptions there, but people just forgot that these assumptions are not true. And it also, in maximum likelihood, which is a horrible way of doing things, it's basically because you assume that everything is independent. You assume that even when you're doing time series regression, that observation 1 is independent of observation 2. That's bullshit. That's like saying, you know, last year I was not 1 year younger than I am today. Of course I was. And that's important. All of those things that are temporally related are extremely important. And the reason why I'm saying this today is that there's no need to cheat anymore. There's no need for these crazy statistical results only. You can state your mind, you can do the inference, and all of it can be done with probabilistic programming. And there are many frameworks for this today, including in Python, and also building on top of TensorFlow, by the way, so there's really no excuse not to do this. And the best thing about it is that it's actually easier than adhering to normal statistics, because in normal statistics, you were taught tools. They said that if you have two populations and they are sort of varying together, then you use this magical tool. If they are independent, then you use another magical tool. Nobody really understood why. They just, but in here is the t-test. In this one, it's a pair t-test. In this one, it's a Wilcox. In this one, you should do a general logistic regression. In this one, you should just do a normal linear regression. In this one, you should use a support vector machine. They are all the same thing. They are not different. They are different assumptions in the likelihood functions. They're different assumptions in your priors. They're different assumptions in the physical structure of your model. That is all. There is no other difference. All of it comes back to probabilistic modeling. And if you can learn how to make these assumptions explicitly, then you have a modeling language without limitations. Then you don't have to know the difference between logistic regressions and linear regression, because there is none. It is exactly the same thing. And that's perhaps the most important thing. The most important thing that I'm going to say today, given that you think it's important, is that you cannot do science without assumptions. That is impossible. Just, you know, this is not my belief. This is just hardcore facts. You cannot do science without assumption. And don't rest your minds until you understand this. So without actually risking something, you can get no answers. So let's have a look at neural networks. I'm sure, how many of you have taken a neural networks class in your days? Okay, then most of you have solved this problem, I'm sure. How many people have solved this problem before? Okay, a few guys and girls. So basically this problem is highly nonlinear, It's a classification task. Your job is to separate the blue dots from the red dots by some line. You can see it's sort of a spiral that's non-stationary. It's quite nasty, isn't it? And a neural network will... How many hidden nodes do you think I have to have in a one-layer neural network to solve this? 10? 20? 50? 100? Let's see. Well, with 10 hidden nodes, I can learn how to separate this. Not great, but there is some signal there. If you use, up here, 30 hidden nodes, you can do a lot better. Not surprising, but it's still not good, because we know that this problem can be solved exactly, right? So with 100 hidden nodes, you almost have perfect classification, right? And if you look at the accuracy table, you will see that the area under the curve is 100% with 100 nodes. Now, what is the problem with this? And this is on a test data set, mind you. Now, the problem with this is that this looks great. This looks amazing. I mean, your job is done, right? Okay, so let's look at the decision surfaces that were generated from these guys. Now, to the left-hand side, you have the decision surface based on 10 hidden neurons. And on the right-hand side, you have the decision surfaces based on 100 hidden nodes. Now, you can see here, does those decision surfaces look good to you? Does it look like they actually have captured what you wanted them to capture? No, it did not. And this is exactly how neural networks work. They are over-parameterized, very flexible mathematical models that will do everything they can to minimize that sum-square error or the cross-entropy error. So there's no penalization for finding statistical-only results. And what is the worst thing with this? The worst thing here is that you see the regions in the outskirts that are colored red? That is a signal that the neural network is sure exists. There was no data out there at all, but it knows that that has a differentiated class. Now, this might not be a problem if you're trying to classify, maybe if there will rain extra much tomorrow. But what if you have a droid with one target? Kill insurgents, let civilians live. What if they identify one of those as, one of those outer regions that just makes sense, that was never part of the training set? This is a truth that has been learned by a network where data never actually showed it this. And there's no penalization for this. And the reason why I'm saying this is not to be, don't use AI or don't use machine learning. In fact, I'm saying the opposite. But what I want to say here is that be responsible. Every time you deploy a machine learning algorithm, you have to understand exactly what it does. Because lack of understanding is the most dangerous thing that can exist today. And it doesn't have to be artificial superintelligence. All it requires is a screw up in the engineer or the scientist who built this network, and it can have dramatic consequences. Especially today, in the time of self-driving cars and all these things. And this here, I will show you another example of why I think that this is interesting. So this is just a representation, and mind you, this is only a single-layer neural network, by the way. No, super deep structures where we would have even more parameters. So I just want to show you that this problem here, represented in Cartesian coordinates, is what was being fed to the neural network. And what the neural network should have realized is that in polar coordinates, it looks a lot simpler, doesn't it? Now, I know that problem. I can separate that with just one hidden node. And this is my point. You can over-parameterize and throw a lot of data at things, but if you start to think about the problem at hand, and if we teach machines to learn how to think, how to reason, how to look at data, instead of just number crunching. And this is why today I'm not scared of artificial intelligence or artificial superintelligence, because I could have solved this in half a second. Even if you don't have a degree in physics, you should realize that these are just two sine functions with increasing radius. It's not hard. But a neural network would never get this, nor would any other machine learning algorithm, by the way. Impossible. because they don't work that way. That's not their goal. So we can't be angry at them for not solving that. I just want to show you a take on probabilistic programming with this, and also explain to you what probabilistic programming is. It's basically an attempt to unify general purpose programming, and by general purpose I mean like Turing complete programs that we all like because they can basically compute anything, and marrying that with probabilistic modeling, which is what everyone should be doing. Everyone, whatever model you're creating, you are doing probabilistic modeling. You just accepted a lot of assumptions that you didn't make. And that is a realization that even though you can choose not to care about it, you have to know about it. You have to know the assumptions behind the algorithms that you're using. And that's why, even though it's very tempting to fire up your favorite programming language, load scikit-learn or TensorFlow or whatever framework you're using, MXNet, doesn't matter. It's still important to understand the concept. You don't have to be an expert in the math behind it. That's not what I'm saying. But you have to understand conceptually what they do. And more importantly, what they don't do. Because that makes all the difference. So this is just to say that you could have written this model a lot easier. Now this is also a breaking point of HTML5 presentations, by the way. This is actually really supposed to be on the right-hand side. So thank you, Windows. Even so, that few code up there is basically a probabilistic way of specifying the model that solves it exactly. And this can be expressed in a probabilistic programming language. The neural network I wrote to fix that took a lot more coding, I can assure you. The take-home messages here is that if you view things, if you go back to basic and view them as what they are, probabilistic statements about data, about concepts, about what you're trying to model, you gain basically a generative model. You gain an understanding of what is actually happening. And that also means that you don't get any crazy statistical-only solutions due to identifiability problems. And this is something we really have to get away from. Identifiability is something that will be problematic. So I'm not going to talk about deep learning. I just want to show you what it is, but I think you've had enough talks about that. So max pooling and all of that, we can. I'm pretty sure we can skip. What I do want to say, though, that neural networks per default are degenerate. And what I mean by that is that the energy landscape that they're running around in, where they're trying to optimize things, there are multiple locations in this energy landscape corresponding to the parameters that minimizes the error. And they're equivalent, but they correspond to very different physical realities. So how's the neural network supposed to know? And this is not something that that we can design our way out of, because the whole idea with the neural network is this degeneracy, because the optimization is such a problematic space. And I just want to visualize with a simple neural network here why this happens. You can see these two networks describe exactly the same thing. They solve exactly the same problem, but the parameters are different. And that's why if you take it from x1 and go to the hidden 2 and hidden 1, you can either have weight 1, 1 be equal to 5 and go to hidden node 1, or you can have weight 1, 1 be 4 and go to hidden 8. So if you basically turn this on its head and shift around these weights, you get exactly the same solution. Now this is one source of degeneracy, and there are many of those. So just imagine now that you're stacking a lot of layers on top of each other. You're having hundreds of neurons. How many permutations do you think you will be able to reach? A lot is the answer. I didn't do the math, but just trust me, it's a lot. So in energy space, in one dimension, it looks like the one on the left-hand side. You see two distinct points that are equivalent in the solution space, and you cannot differentiate between them. This is also why regularization is such a good idea in neural networks, because it basically forces you to enter one of those attractors. And in two-dimensional space, you can see that it corresponds to these two attractors in this colorized plot. And then if you visualize this in all the dimensions that the neural network is actually operating in, which is typically thousands of dimensions, then you can just imagine how many of those attractors you have, and different depths of those attractors. So I want to end my point. If you missed my point, I tried to state it several times, but sometimes I'm very clumsy in the way I state things. So I'm going to be very blunt. This is one of the best neural networks at given 2016 or 2015 was a version of the Linnet that was trained to recognize digits. And it does that perfectly. Like we said before, we're so far in this area about perception that we don't have to worry about not being able to do it. It's actually done. And it's much better than humans at recognizing these things. Okay, so let's put it to the test, shall we? Let's generate some random noise images and ask it, what is this? And in every single image here you see, the network is 99% sure that it's a 1 versus 2 all the way up to 9. So all the 4 images under the 0, it is convinced with a likelihood of 99% that this is a 0. Can you in any way understand why this is a 0? I can't. And nor can the network, because it was never penalized based on the fact that you're not allowed to find structures that does not sort of dispute your data. It has no briefing that it has to stay true to some sort of physical reality. And this happens. Now back to my point. What if it's not the number 0? What if it's recognizing the face of a known terrorist with a kill on sight command? And this is just numbers, ladies and gentlemen. Imagine the complexity of faces. So this is again to point exactly how dangerous this technology is if you don't respect it. And it's not about the machines being too intelligent. It's about us not being stupid. That is really important to remember. We have a responsibility to build applications that do not have this confirmation bias in them. And that is something I hope that all of you will think of when you go out and build the next awesome machine learning application. Because I can't see any numbers in these images anywhere. And if you want to, you can read the paper by these guys that I said. You get the slides afterwards. And it's a very interesting paper. They basically tried all they could to see how the network could generalize with things it hadn't seen before, and in different areas of what it was supposed to see. Another thing I want to say is that events are not temporally independent. Everything that you do today, everything that you see today, hear, perceive, think about, is affected by what you saw yesterday. And it's the same in data. Data is not independent. You cannot assume that 2 data points are independent. That is a wild and crazy assumption that we have been allowed to do for far too long. And this is just a small visualization from the domain that I was working in, where we were trying to solve how a TV exposure affects the purchasing behavior of people moving into the future. And of course, if you see a TV commercial today, it might affect you to buy something far into the future. And it might affect no one to do something today. And that's causal temporal dependencies that also needs to be taken into account. If you think about causal dependencies, and if you think about concepts, if you really think about structure of things, then you end up with something that looks like a deep learning neural network, but where you actually have a structure that is inherent to the problem at hand. And that's basically you're forging connections between concepts, between variables, between parameters, that sort of solves the problem at hand, but that doesn't have this over-parameterization. And this is a visualization of one of the models that we're running in Blackwood for one of our clients. And this is sort of the complexity that you need to have to solve the everyday problems. Every node that you see here is basically a representation of a variable or a latent variable, and the relationships between them are basically the edges. And basically, there's no point in this thing spinning. I just thought it looked cool. And it helped me raise money back in the days. Actually, the spinning, I think, was the differentiator, because in one of the pitches I did, it didn't spin, and we didn't get those money. And then all of a sudden, it was spinning, and we got those money. I don't know if that's, all the reason, but the spinning, in my mind, helped. So, but there's no visual improvement based on that. How many people have seen this before? Okay, well, that's just no fun. Okay, but before I saw it the first time, interestingly enough, I had not seen it. So the problem here is that you're supposed to judge whether A and B, the squares there, are of the same hue or not. And from my point of view, they are extremely differentiated. They look very differently. But The problem is that they're not. They're actually the same. And the reason why a lot of people think that they are different is because we are predicting based on the shadow that is being cast from a light source that we know where it is because we have recognized this pattern earlier in our lives. That is also a kind of confirmation bias, but it's a good one because that's what allows us to actually live our lives. And sometimes we are wrong, like in these contorted images, but it does prove a point. That's because our brains are very biased based on what we know already, and we do predictions based on what we know. So basically, probabilistic programming, what that is, it basically allows us to specify any kind of models that we want. No, you don't have to think about layers, you don't have to think about the pooling, you don't have to think about all the wording. All you have to think about is that you specify how variables might relate to each other, and you specify which parameters that might be there and how they are relating to the variables at hand. And if you have that freedom, then there's nothing you cannot model. The problem with this is that you cannot fit that with maximum likelihood. You cannot adapt that because you can't assume independent observations. You can't assume that everything is uniform. You can't assume, well, you can, but it's not very smart. You can't assume that any given parameter has a possible value of -infinity or +infinity. Now, this in general just makes no sense. Just think about the fact that you're supposed to predict the house prices, for example. If you allow your model to predict something which is negative, then you have something that might make sense again in statistical space, because there's no reason why you shouldn't be able to mirror things, right? You just look at the positive part. But what about the part of your model that says that negative sales prices are also positive? That's just nonsense. And these things you shouldn't allow. So that's why you should specify your priors and the concepts of your models very rigorously. And the best thing about probabilistic programming is that we no longer have to be experts in Markov chain Monte Carlo. Before you had to do that, but today you don't. You don't have to understand what a Hamiltonian is in this space. You don't have to understand quantum mechanics. You just have to learn how to program a probabilistic programming language, which is very easy, by the way, super easy. If you know Python or R or Julia or C++ or C or Java, learning how to program a probabilistic programming language is a walk in the park. And it's still Turing complete, mind you. There are a lot of different things we get out of this. We can get the full Bayesian inference with the Markov chain Monte Carlo through algorithms such as Hamiltonian, Markov chain Monte Carlo, the no U-turn sampler. That's what you really want to do. The problem with this is that still today it takes some time. There's another emerging tool that's called automated differentiation variational inference, which is just a lot of different words that says that turn the inference problem into a maximization problem. And we have gotten somewhere with that, which makes these inference machine a lot easier to fit. The best thing is that also the math library already has this automated differentiation, so you don't have to be experts in that either. Again, all you have to do is learn a probabilistic programming language, or learn a framework in Python that supports it, like Edward, for example. There are many other frameworks that do the same thing. A note about uncertainty. Now, what if I gave you a task? Your task right now is to take $1 million American, and you're going to invest them in either a radio campaign or a TV campaign. And I'm going to tell you that the average performance of each campaign has been 0.5. So the return on investment for an average radio campaign has been 0.5. The return on investment on an average TV campaign has also been 0.5. Now my question to you is, how would you invest? Does it matter? Well, based on this information, I would say I will just split it 50-50. I mean, why not? They have the same performance, right? But what if I also told you that actually, if you look at RI as the distribution, if you look over all the different radio campaigns that have been run and all the different TV campaigns that have been run, if you look beyond the average and look at the individual results, what do you have then? Well, then you have that radio, for example, and TV, they both have had historically a return on investment of 0, which basically means it didn't work. That could be like some of the commercials you see on TV sometimes that are less than good. You know, sometimes you see these naked gnomes running on a grass field, and they're trying to sell cell phone subscriptions. I never really understood the connection, but that didn't work, I'm sure. I didn't quantify that, but it didn't work on me. Then I'm going to tell you that the maximum radio and TV performance that has been observed is that radio has had in its history a return on investment of 9.3. Meanwhile, TV has only had 1.4. How would you invest now? Would you still split it 50-50? I wouldn't. Now, what if I tell you that this is probably not the real solution either? In order to answer this question, you have to ask another question in return. You have to ask the question, what is the probability of me realizing a return on investment greater than, for example, 0.3? Let's just take that. That is what I want to achieve now. Now we have specified what our question is, and then we can give it a probabilistic answer. And then the answer to this question is that it's about 40% probable for radio to get a return on investment for any given instance above 0.3. But it's about 90% for TV. How does that go hand in hand with the fact that radio has outperformed TV historically as a maximum, and they have the same average? Well, it's because of the fact that things are distributions. Things are distributions, and they are not Gaussian. Now, this here is the source of failure of every statistical method that you probably have tried before, because it assumes that everything is symmetric and Gaussian. Nature makes no such promise. It has never said, thou shalt not use Cauchy. Never has that been part of any sort of commandment or information given to us by nature. There is nothing special about the Gaussian distribution. There is a few things special about it, but you know, let's just ignore the central limit theorem for now because of the fact that we don't have enough data to actually approach that anyway, so let's just ignore that for now. Now the point here is that the distribution of radio looks like this, and the distribution for TV looks like the one below. And here you can see they have the same average, very different minimas and maxima, and very different skewness. And this is why you cannot make optimal decisions without knowing what you don't know. You cannot make optimal decisions without knowing uncertainty, even though if you knew the average performance. Average performance is such a huge culprit in bad science and bad inference. I cannot state this enough, and that's also why you should never, ever, 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 ever treat the parameters of your model as if they were constants, because they are not. It's also not interesting to ask the question, how uncertain is my data about this parameter, about this fixed parameter? Also a nonsense question, not interesting. And that is why we have to go back to basics and do it right, because until we do, we will never get further. So if I can tie this all together, I created sort of a way for you to start playing around with this. I made a Docker image, basically, which is called R Bayesian. R is the host language, but you can basically use whatever language you want. It doesn't really matter. What I want to show here is basically how easy it is to deploy a Docker container with a Bayesian inference engine that can model any problem known to man. There is nothing you cannot do with this framework. Nothing. It is more general than anything that you have ever tried, because it can simulate everything that you have ever tried, and most of the things you have ever tried comes from probability theory. And this is just a pure application of probability theory. So this is a very easy way to just snap that Docker container, and the best thing is that the functions you write in there are automatically converted to REST APIs that you can expose through this Docker service. So you have a REST API ready, inference machine that is very much true to the scientific principle with no limitations, and the only thing you have to pay for it is that you have to think twice. Now, for those of you who doesn't like R, I can make one version with Python or Julia or whatever. It's not about the language R. What I really want to convey is that modeling needs to be rebooted. We need to think again on how we define our models, how we specify our models, how we think about our models, how we relate to our models. We can never, ever relate to our models without uncertainty. We will always fail. That's why I think that playing around with this is a good way to learn more about these things. This is just an example of how you would actually use this. So I wrote a very, very stupid container that it's called stupid weather. And it's stupid because it always gives you the same answer. So no matter what you send in as parameter, it always gives you something stupid. That's just to show you how you write a function. It's not supposed to convey any intelligence. It's just a placeholder. It's just boilerplate code for you to ingest your algorithm. But it shows neatly how you're transforming this to a REST API. And it's as simple as this. Just Docker run, and then you have it. So even if you're not, a back-end developer or a full-stack developer, it's still easy to deploy and run your own solutions. And a Docker container can run anywhere in the cloud. It can run on Google, it can run on Amazon. I think even it can run on Microsoft's cloud, Azure, probably. I didn't try that, but I would assume that they can run Docker containers. So, if I can leave you with one conclusion, it is basically think again about everything that you were ever taught. Every statistics class you had, every applied machine learning class, all of it. Rethink it. Reevaluate it. Be critical to whatever you were told. Because I can assure you that in most cases it was a flatulent lie. And that lie didn't happen because of the fact that people wanted to lie to you. It's based on ignorance. And it's based on, decades of malpractice in this field. Because computation has caught up with us. Before, it was okay to do what was done because we had no other choice. Today, no longer okay. We have all the choices in the world. It's not hard getting a computational cluster with 200 gigabytes of RAM and 64 CPUs. Or even 5,000 GPUs. Those things are at our disposal. We don't need to take the same shortcuts as we did. Dangerous shortcuts, no less. So, I hope you will think about that. Another thing is that whenever you're solving a problem, I would like you to think about that whatever problem you're solving, whatever machine learning application you're writing, it is an application of the scientific principle. Please stay true to that. There's a reason why we have it. Science is a way for us to not be biased. Science is a way for us to discover truths about the world that we live in. This should not be ignored or taken lightly. And that's why, crazy people like Trump can get away with saying that there is no such thing as global warming, because he does not adhere to the scientific principle. So, you can either be Trump or you can stay true to the scientific principle. And those two are the only extremes, my friends. So, another thing that I want to say is always state your mind. Whatever you know about the problem, I assure you that that knowledge is critical and important. Do not pretend and fall into this trap. Oh, I want to do unbiased research. There is no such thing. No such thing. Understand this. There is no bias-free research. There is no scientific result that can be achieved without assumption. You are free to evaluate your assumptions again. Restate them. That's good. That's progress. That is science. But before you're observing data, state your mind. And you have to, because otherwise, you got nothing. You got a result out, but that was just picked out of thin air. It's nothing special about those coefficients that came out. Nothing at all. And until people realize this, we will still have applications that believe that Central Park is a red light. And it is not. Even though that might look like it from a different scale, we need to do better. And we can do better. And maybe the most important thing of all is that with this framework and with this principle of thinking, you are able to be free, you are able to be creative, and most of all, you are able to have so much more fun building your models because you are not forced into a paradigm that someone else defined for you because it made the math nice. Thanks.
I think we have time for one question. Somebody asked, where can I read more about this? Any good resources?
Yes, there are a few great books that I can solely recommend, and I will do them in mathematical requirement order. So if you're a hardcore mathematician or a theoretical physicist or anyone with a computational background with a deep understanding of mathematics, then you can go directly to read a book called The Handbook of Markov Chain Monte Carlo. That is a very technical book, and it describes the processes behind the probabilistic modeling. If you are a little bit less mathematical, but still has quite a bit of mathematics, you should read the section about graphical models made by Bishop in a book called Machine Learning and Pattern Recognition. But the most important book of all, perhaps, to read is one of the books called Statistical Rethinking. And that book explains a lot of the concepts that I've been badgering now that, somewhere along the line we just got lost. That has both text that is consumable by people, and it has a little bit of math, so you can sort of put it in context. Those are really the books I would recommend in this.
Okay, thank you, and I'll tweet the resources to the hashtag GotoCph.
Great.
Thank you, Michael.
Thank you.